Today we move on to recursive sequences. The sequences we looked at in the last video are called explicit. They had formulas that looked like the following. The reason they were called explicit is because you could put a value in for n and find the term explicitly that n represents. So today's sequences are going to look a little bit different. A recursive sequence allows you to find the nth term by doing something to the term before. And so a recursive sequence will always have two parts. It will start out by stating what the first term is. The second line of the sequence will start out saying the a sub n, the nth term of the sequence, is what you get when you look at the term before. So this right here, a sub n minus 1, means the term that came before. And then, since it's an arithmetic sequence, we're going to add the d value. Okay? So we're just learning a new way to write a sequence. So here's an example. Let's look at 5, 8, 11, 14 as our sequence. We know that the difference, what we're adding each time, is 3, and the first term is 5. So the recursive sequence for this set of 4 terms is a sub 1 equals 5, a sub n equals a sub n minus 1 plus 3. Okay, what I want to bring to your attention is that the a sub 1, the a sub n, and the a sub n minus 1 will always be there. The only thing that will change will be the difference and the first term. Okay? Let's go ahead and do the same for a geometric sequence. Okay, so let's go ahead and this time look at the values 4, 6, 9, 13.5. And remember, to find the common ratio, what we need to do is take the second term and divide by the first term, and 6 divided by 4 turns out to be 1.5. We might just want to check to make sure that it truly is a geometric, so you could also take the third term and divide by the second, but I think it's pretty easy to see that each time we're multiplying by 1.5. And so the recursive sequence for this set of terms would be the first term is 4, and to get the nth term, we look at the term before and we multiply by 1.5. So let me just say again that the g sub 1, the g sub n, and the g sub n minus 1 will always be there exactly as they are, and what changes will be the first term and the ratio. What we realized right from the beginning is that recursive formulas are not as useful. So if I have the recursive formula, or let's start with an explicit formula, a sub n equals 3n plus 2, and I wanted the 100th term, because it's written explicitly, we can simply plug 100 in and say that 302 is our 100th term. If I have that same sequence written recursively, all right, so the first term is 5 and the nth term is the term before plus 3. If I wanted the 100th term, that was my question, and I only knew the recursive sequence, well, I would first need to find the 99th term to add 3 to it. And in order to get to the 99th term, I would have to know the 98th term. So when we look at an example like this, we find out that the recursive definitions of sequences are not as useful, and we don't use them as often, but I do want to show you one example of why we do need them. So far all of our sequences have been arithmetic or geometric. Sometimes we have situations that occur in real life that it doesn't turn out we're adding the same thing each time, multiplying by the same thing each time. So here's an example of a problem. Let's talk about this country that has a starting population of 500,000, and each year a couple things take place. First of all, there's a 2% growth in the population each year. In addition, because it's a really great place to live, there are 20,000 immigrants moving to the country. And so we want to describe this situation and find some information, maybe figure out in 10 years how many people would be there. So not easy to come up, in fact impossible to come up with an explicit sequence that would describe this. So instead what we're going to do is describe it recursively. So we're going to say the population at time 0 was 500,000. And then to find the population in the nth year, we're going to look at the population the year before, and we're going to do two things. First, we're going to multiply it by 1.02 to represent a growth of 2%, and then we're going to add those 20,000 immigrants in. Okay, so this is a recursive sequence. Then we could find maybe perhaps p sub 5. Of course, we would have to find p sub 1, p sub 2, 3, and 4 in order to get to 5. But we are able to use a sequence to describe a situation that's a little bit more complicated. Okay, great. We'll see you in class.